Quadratic functions and transformations. So a quadratic function has a graph that's a parabola. So you may recall from last year's class that a parabola is a U-shaped curve, so it would look something like that. And the equation for the quadratic function is f of x or y equals ax squared plus bx plus c. So you'll know that you have a quadratic function if you see an equation in that form. Just like with linear equations, we were writing them in different forms. We had slope-intercept form, we had point-slope form, standard form. But you can write a quadratic equation in a couple of different forms. The one we just looked at, standard form, ax squared plus bx plus c. And then the vertex form of the quadratic function is f of x or y equals a times x minus h squared plus k. Now you probably noticed that this should look familiar to you. It resembles the absolute value function that we looked at in the last chapter. With quadratics, you have an axis of symmetry because they are symmetric, right? If you were to have that vertical line that runs through the vertex of the parabola, just like we said with absolute value, if you were to fold the piece of paper on that line, then the right side of the parabola would overlap the left side of the parabola because you have symmetry. And just like with absolute value, notice that the equation for the axis of symmetry is the same, x equals h, and also that the vertex is the same in a parabola, hk. So you should recognize some familiarity between the two types of functions, and as long as you understand the basic concepts, then transformations and picking out different parts of the equation shouldn't be too hard. Here we see the parent function of a quadratic graph. So here we have f of x equals x squared, which is the parent function. So that's our parabola here in blue. And you notice that they show us an axis of symmetry of x equals 0. That's the red line here. And again, if we were to fold the paper on this red line, the right side of the parabola would overlap the left side here. Notice that in the parent function, the vertex is at 0, 0. Again, axis of symmetry at x equals 0. So that's the basic concept for the quadratic. Here are some other concepts that relate to transformations. And if you recall from the absolute value functions, they're going to be very much the same. If you take a look here at the graph on the left, it's showing you a reflection. And again, when a is positive, you'll have the parent function here, y equals x squared. But if a is negative, as shown here, the graph flips over the x-axis, so you have a reflection over the x-axis. In the middle graph, they're showing you a parabola that's stretched. Again, when a is greater than 1, we have a number greater than 1, it's going to stretch. The parabola will become narrow as it stretches out. So just like with the absolute value, you'll have a stretch if a is greater than 1. And similarly with the compression, recall that the absolute value function had a compression when a was a value between 0 and 1, in other words, a decimal or a fraction between 0 and 1. Same thing holds true with the parabola. When a is a fraction or a decimal between 0 and 1, the parabola is pushed down and it widens from the compression. A couple of additional things that we didn't see with the absolute value function, but we have here with the parabola, is that, again, if a is positive, you'll notice that the opening of the parabola is up on top and the vertex is at the lowest point. We call that a minimum value when the vertex is at the lowest point. If a is negative, then the parabola will open up at the bottom and the vertex will be at the highest point. That's our maximum and maximum value. Now the maximum value, the value itself, is the y-coordinate of the vertex. So here the y-coordinate of the vertex is that maximum value. So here they talk about graphing each function and how is each graph a translation of the parent function, f of x equals x squared. So if you recall from the rules of transformations with the absolute value function, if we look at g of x equals x squared minus 5, even without graphing the function, we would see minus 5 outside of parentheses, so we would know that the parent function is being shifted 5 units down. So down 5 units. Here in part B, we're subtracting 4 within the parentheses. Inside the parentheses is a horizontal shift. And what we see here is that it's moving to the right by 4 units. So we could take a look at that in the graph and verify that. If we go to the calculator here, so we have our x squared minus 5. We would expect it to translate down by 5 units, and sure enough, it translates down 5 units. We had the x minus 4 squared, and we said that would move to the right by 4 units, and it does exactly that. So again, same rules apply when you're dealing with quadratic functions that did with absolute value functions. Again here, how is it a translation of the parent function? So with the x squared plus 3, again, we would expect it to go down by 3 units. And with the x plus 1 squared, we would expect it to go to the left by 1 unit. Remember that x plus 1 is the same as x minus -1, and that -1 here is telling you that it's moving to the left by 1 unit. Here they're kind of putting everything together. So we have this equation. And they want us to find the vertex, the axis of symmetry. They want us to tell whether there's a maximum or a minimum value here, and they want the domain and range. So what we have to remember here is that for the vertex, we said the vertex is going to be the coordinates h and k. And in this equation, h is 4, k is -2, so our vertex will be 4, -2. For the axis of symmetry, we said the equation is x equals h. Well, in this equation, x equals, well, h is 4. We already identified it as 4, so x equals 4 is the equation for the axis of symmetry. Then they want to know if we have a maximum or a minimum. Well, that's going to be determined by the value of a. We said if a is positive, that parabola is going to open up on top, and the vertex is going to be at the lowest point or a minimum point. So this one has a minimum. And they want to know the value. Well, the value is whatever k is, whatever the y coordinate of the vertex is. So in this case, it's -2, so our minimum value is equal to -2. And then lastly, they want the domain and range. So the domain is very easy. In every quadratic function, the domain is always all real numbers. For the range, we have to look at the vertex. It's all going to depend on where the vertex is. So here, our vertex is at 4, -2. Our minimum value is -2. So if you think about it, just roughly, the graph will look something like this. So we have 4, -2 as the vertex here. So when we're looking at the range, we're looking at all the y values that are encompassed by the function. So if you look at this graph, there is no graph below, that's a -2 there. So there's nothing below -2. The graph only appears beyond -2. So we could say that the range then is y is greater than or equal to -2, right? Because we only have graph from here up. So anytime they want the domain, again, it's always all real numbers. For the range, it's basically this. If you have a minimum value, then the range will equal y is greater than or equal to whatever the value of k is. When you have a maximum value and they want the range, then the range is always going to be y is less than or equal to k. So that's how I would remember to get the range correct, by looking at whether or not you have a minimum or a maximum value, setting up y and k, and then just knowing which inequality symbol to put in between them. Again, here they want the vertex, axis symmetry, minimum, maximum, domain, and range. So again, we're going to take a look here for what the coordinates of the vertex are. So x plus 1 tells you that it's x minus -1. So h is -1 and k is 4. So the vertex is at -1, 4. The axis of symmetry, again, is x equals h. Since h is -1, we have x equals -1. Now they want to know, does it have a minimum or a maximum? So the thing to key in on is the value of a. So we see a is negative here. When a is negative, we've got a maximum value, right? Because when a is negative, that opening of the parabola is going to be at the bottom, and your vertex is going to be at the highest point. So that highest point is your maximum. And the value we said was whatever k is, so our maximum value is 4 in this case. Okay, so domain, again, very easy. It's always all real numbers. And then for the range, we said take a look at that vertex. So we have a maximum. We said for maximum, it's always y is less than or equal to, and that's going to be the value of k. Since k is 4, then y is less than or equal to 4. Okay, so now they're asking about transformations. And again, the rules for transformations are the same as they are for the absolute value function. So we're starting here with y equals -2 times x plus 1 squared plus 3. So when you're doing transformations, you got to remember, start at the very left, and then work your way to the right. So the first thing that we see starting at the left is a negative sign. And you always have to remember to separate the negative sign from the number. So we're just dealing with the negative sign right now, and that negative sign tells us that there's a reflection over the x-axis. The next thing we take a look at is the number 2 itself. And the number 2 is telling us we have a value greater than 1, which means we have a vertical stretch by a factor of 2. The next thing we see is the x plus 1 inside the parentheses. Inside the parentheses is telling us there's horizontal translations going on. So since it's x plus 1, again, we know we're dealing with x minus negative 1. So if h is negative 1, that means we have a translation to the left by 1. Translation to the left by 1 unit. And then finally, we see a plus 3 at the end of the equation, and that plus 3 tells us that we have a translation that's moving up 3 units. So that's everything that we see coming out of that equation. So again, the negative is telling us the reflection over the x-axis. The number 2 is telling us we have a vertical stretch by a factor of 2. The x plus 1 tells us that it's translating to the left by 1 unit. And finally, the plus 3 is telling us that the parent function is moving up by 3 units. Same thing here. We're looking for the transformations. So again, starting at the left, we don't see a negative sign, so there's no reflection taking place at all. We'll just leave that out. We'll start with the 2 itself. The 2, again, tells us that we have a vertical stretch. So we'll go with a vertical stretch by a factor of 2. The x plus 2 is telling us that it is translating 2 units to the left. Okay, again, this is the same as x minus negative 2. So that negative 2 tells us it's going to the left. And then finally, we have minus 5 at the end of that equation, and that minus 5 at the end of the equation tells us that it translates 5 units down. So very similar to the absolute value rules for transformations. If you have those nailed down, then this should be a piece of cake. All right, so good luck with the homework, and we'll check it all out next time we meet.